you know. So anyway, so I'd like to just give you a brief introduction of this meeting, why we are here and what is expected of us. Jim gave you some copies of my presentation, but it's like 1 week old, so I have a little better one, I think. So the IAEA, the agency is based in Vienna. We have about 2,400 staff members, and it's supported by 157 member states for various things related to atomic energy and nuclear programs. Our unit exists to support for fusion program worldwide, but the fusion program has a dilemma. Basically, we are trying to put the burning sun into a box, but the problem is that we do not know how to make the box. So fusion research requires a huge amount of material data, atomic, molecular, and plasma surface interaction data. That's why the unit was formed in 1977 to review the progress and achievements of all the AMPSI data for fusion programs. And so the way we do is to stimulate international cooperation in measurement, compilation, and evaluation of this data for fusion. Our activities include like coordinating research projects to do this data work, and we publish books, bulletin, reports, technical documents, and so on. We also maintain knowledge base and also databases. And also we organize the technical meetings like this, workshops, and we invite consultants to do data work and so on. We interact with many different communities, of course, the fusion users, fusion laboratories and universities in fusion program. We work with national data centers in different member states. We also work with you, the atomic and molecular physicists, the data producers. So the biggest issue in fusion program is ITER. It's going to be the biggest tokamak ever built. The price tag today is 15 billion euros, but it's going to be increased probably. It's paid by 7 member states, so everyone except for 1 or 2 people here are paying the taxes for this. So for this project. So the construction is supposed to be completed in 2020. They are still building, but they're also doing some design work and so on. It's going to be a lot of steel, literally tons of steels, and the most important thing is that there will be divided region here that has to withstand the heat flux of 10 megawatts per square meters. So there are a lot of atomic and molecular data needed to design this thing. And you know, coming from UN, I have to say this, it's a huge investment for the sustainable future of mankind. So we have to do this. For ITER design operation, there are a lot of evaluated recommendation data are needed. So that's the whole point of this workshop, evaluated and recommended data for fusion program. That's because, you know, when you design something, design the fusion reactor, you have to do this egg transport code modeling. And for small research, tokamak, the reactor, it will take only 1 day to do a code, but it will take few weeks for the jet, which is the biggest tokamak currently. But for ITER, it will take 3 months. So you really want to reduce any kind of uncertainty coming from this fundamental data by providing the recommended data for this reactor. And Detlef Reiter is going to talk more about the fusion and also the data needs in this. It's all because of this, the huge reactions, many reactions in plasma chemistry occurring at the diverter region and also around the layers around the box. So we have been involved in organizing meetings since like in 2 years ago. We started out with some consultancy meeting and several consultancy meetings and technical meetings. And then finally, this is the last of the series, and you can see that many of you in this audience have participated in the whole organization of these meetings. And one of the important meetings was like September 2012 in Korea. we really talked about how to increase the evaluated and recommended data for fusion program. We talked about it in general in many different aspects: theoretical data evaluation, experimental data evaluation, sensitivity analysis, data evaluation techniques, and so on. We had more than 20 participants from 11 countries. We have proceeding papers here published in fusion science and technology. So one of the biggest conclusion was that in order to increase the evaluated recommended data, we really have to work with community, and there should be a community consensus to do this. To achieve this goal, we have to disseminate some definitions of terminology in evaluation and recommendation. We also have to disseminate materials with the critical analysis skills so that the data producers themselves can evaluate their own data, and also involve community in this recommendation and evaluation of data. And after this meeting, we have several groups who are reviewing the data. For example, like in last December, we organized this meeting for nitrogen molecule where Johnson and Slava were there. People were evaluating the electromolecule data together to recommend it. The other issue that we identified was the biggest hurdle for any kind of data evaluation right now is the lack of uncertainty estimates and theoretical data. So I'm going to I'm going to talk more about these 3 points now. Basically, terminology has been already defined for us by the BIPM, the Meteorology sort of International Organization, and already terminologies of measurements have been defined in this international vocabulary of meteorology or measurements in 2007. There is a guide also to the expression of uncertainty in measurements. So the concept of measurements and errors and uncertainties, they all have changed since the 1980s. Before 1984, they used to use error approach, which means that people are trying to measure true value of the quantity of your interest. So whatever imperfection of your measurement is said to be an error, because you identified true value and you measured many things around it. So since you know the true value, you define errors. But in many cases, you will never know what the true value is. Sometimes there is no true value. So in a sense, it's not useful to say when you do not know true value, you cannot define error. So basically, after like 1980s, the international community agreed that it's going to be measured value with uncertainties, where the true value will be likely to lie in. So that's the new concept, or it's already 20 years, but there was a change in conceptual change in values and uncertainties. So that's what we have to work with in terms of measurements. Unfortunately, the VIM and GUM, they all address issues for physical measurements, experimental measurements, but not for the theoretical data or measurements. So, but the issue is the same in a sense, and there has been a movement in various communities to try to assess the theoretical data or modeling of physical processes. So I sent you a link of the National Research Council of USA government report. The title is Assessing the Reliability of Complex Models. There they identify 3 different components in the critical assessment for modeling of complex models. So the true system or the true value that you're trying to measure, that system has to be represented by mathematics, and then the mathematical model is now represented by computational models. So how good this transition is, or how good they agree, is the process of verification. So one has to verify their computational model. Once you have the results from computational model, then you have to know how close they are to the true system. That will be the validation or evaluation in our terminology. And then one has to come up with the uncertainties, because you have the result, but you have to also provide the the uncertainties associated with your results. And so there has been many communities, reports, working groups now. I know that Frederick is going to talk about this a bit in his talk. So I just also learned that the NSF Division of Mathematics, the advisory committee has already recommended that they should encourage the interdisciplinary interaction between the scientists and mathematics on these issues already in 2010. So I'm not going to talk much about the Bayesian update, but it has been used as one of the methods of uncertainty quantification. So Slava is going to talk about the approach, because the Bayesian update has been used for nuclear data evaluation and assigning the uncertainties for nuclear reaction data. So Slava is going to talk about it. But the thing is that basically you have a prior model which start out with big uncertainty and some value, but by adding the experimental data or some kind of likelihood information, you can reduce the uncertainty, and also you can get much better values from this Bayesian theorem. So this, I got it from Dave Schultz's presentation. I find it really interesting. Before 1970s, before there's no measurement, we have orders of magnitude different theories, but as soon as we have measurement, we all kind of in the vicinity of experimental data. So in a sense, this is Bayesian update, you see. We have a prior, and then we have likelihood of the experimental data. But we want to do that more systematically, right? And so what if there is no physical measurement? And what's the best way to assess the quality of this theoretical data? And that's the goal of this meeting. It would be really nice if it had this kind of uncertainty, then it wouldn't be that embarrassing. Yeah? So anyway, so this is one of the things from the GUM, the Guide of Uncertainty Estimate. So the way it works is that you have to model your measurement or theoretical model or computational model as a function of many different components. And these components will have uncertainties associated with this sort of subcategories of this, or sub-classes, problems of this model, and then you can identify this, and then you can work on the uncertainty estimate of each individuals, and eventually you can get the total uncertainty. So we organized a meeting last year, and Klaus was there, Johnson was there. We talked about how to develop guidelines. But eventually we just end up talking about strategies. So it has to, the guideline has to depend on many things, like target, resolution, observable of interest. You had some ideas about atomic structure, how to develop guidelines, look at the state distribution, operators, basis sets, and so on. After this meeting, Per Johnson, who was in our meeting, has interacted with his collaborators to write 5 papers on the uncertainty estimates of atomic structure in the new open access journal Atoms. So you can find some information. For atomic collisions, one of the important things was that there should be a distinction between the computational intensive codes and production codes, and also benchmark result can be used to set up some uncertainties or basis. It's very common, and also different methods. Very similar in molecular collisions, again, but different methods. It's important to compare different methods solving the same problem and try to come up with some uncertainty, some systematic errors or whatever. So that's how this whole meeting came about. And so I have worked with ITAMP and Jonathan, Klaus, and Dave to bring you a number of people working on these electron collisions with atoms, ions, and molecules, electronic structures, and so on. We would like to come up with some ideas, reasonable uncertainty estimates for calculations using various methods. So as I described, I don't think this will happen in 3 days, but this is going to be just a working discussion among ourselves, within the community, but I would like you to think about what the possible uncertainty sources in your method in this. And so, as I said, the desirable output will be guidelines for estimating uncertainties. We have really great, exciting agenda here, schedule, and I'm so excited about the discussion sessions that we're going to have. And so we have discussion on heavy particles on Tuesday and electronegative molecules led by our organizers. And I'll finish with the I would like to get some recommendations what IAEA can do to help you in this process. So thank you very much for your attention.